In the previous lecture, we talked about the use of static equilibrium equations for analyzing rigid bodies. For a two-dimensional body, the equations are: these equations relate forces and distances. Therefore, it would be helpful to construct a diagram showing all the relevant forces and distances graphically. We call such a drawing a free body diagram. For example, in the case of this crane, if we were to analyze the system as a whole, that is, if we wanted to calculate the reactions at the base of the crane, then the relevant information would be the two applied forces, the two reaction forces at the base of the crane, and the distances among these forces. To place these forces and distances in proper context, we may also want to draw the outline of the system like this. Such an outline should reveal the points of application of the loads in case they are needed. Since free body diagrams often become a source of confusion when solving problems, we're going to start with a simple case and gradually work toward more complicated scenarios. Consider this bridge. It rests on rollers at one end and pins on the other end. Due to the symmetrical nature of the triangular truss, for analysis purposes, we can view it as a two-dimensional system. Here is a two-dimensional graphical representation of the truss and the load it is carrying. The bridge rests on a roller support at the left end and a pin support at the right end. These supports transfer the load from the bridge to the foundation. Since the bridge is pushing on the foundation through the supports, according to the third Newton law, equal and opposite reaction forces develop at the supports. We refer to those forces as support reactions. In dealing with structures, we often need to calculate their support reactions, so our free body diagram must include these reaction forces. Let's examine the behavior of the pin support. It is assumed not to move vertically or horizontally. This means if a horizontal force is transmitted to the support, then the horizontal reaction force develops at the base of the support, per Newton's third law. And if a vertical force is transmitted to the support, a vertical reaction force develops at the support. But the pin cannot resist a bending moment. That is, if a bending moment develops in the assembly attached to the pin, it would cause a rotation, preventing a resisting moment to develop at the support. So, a pin support carries two forces only, a force in the x direction and a force in the y direction. Here is an example of a pin support at the base of a column belonging to a frame. Here is a gigantic pin support at the base of a bridge. And here is a pin connection supporting a part of a roof structure. A roller support is a bit different than a pin support. Like the pin, the roller resists a vertical force, but it cannot resist a horizontal force. When such a force is present, the roller moves in the direction of the force without resisting it. It cannot resist a bending moment either. So the only reaction force that develops at a roller is a force perpendicular to its surface of contact. Rollers often can be seen in bridges. Here is a roller supporting a beam girder. And here is a set of rollers at the base of a highway bridge. Suppose our bridge is subjected to a single concentrated load of 30 kilonewtons. The load is assumed to be acting at the center of gravity of the vehicle. In order to determine the support reactions of the bridge, we should draw its free body diagram. Our diagram must include the applied load, the reaction forces at the supports, and the distances between these forces. We should also label the unknown forces since we need to write the equations in terms of the force magnitudes. Here, I'm going to label the magnitude of reaction force at the roller as AY and use BX and BY for the force magnitudes at the pin support. And I am going to draw a triangle as the outline of the structure which shows the location of the forces on the bridge. Using this free body diagram, we can easily write three equilibrium equations. Here is our coordinate system. The equations are: solving the last equation for By, we get Then, from the second equation, we get, and the first equation gives us. We are going to examine more challenging free body diagram cases in the next lecture. In the meantime, see if you can draw the free body diagram for each of the following problems. Then write and solve the equilibrium equations for the unknown support reactions.